Back to the AP Chemistry series, and right now I'll be covering electromagnetic spectrums, the atom in its ground state and its excited state, and two famous equations that we'll be using from now on. So, an atom or a molecule exists in its ground state, or the lowest possible energy state. When it has any more energy than its ground state, it is in what is known as an excited state. And an atom losing energy from its excited state to its ground state can result in light being emitted. So let's consider an example. Let's consider an electron, and I'll draw it right here. Let's consider this electron right over here. It is, right now, closer to the nucleus than this electron over here, all right? So when this electron jumps down to closer to the nucleus over here, it is losing energy because there is a principle that you need to understand. The closer you are to the nucleus, the less energy you have. All right. So when this electron jumps down to a lower orbit, such as this one over here, it is losing energy, and it will emit that energy, since it can't be destroyed, as a photon or photons. All right. And that is the light being emitted that we talked about earlier. All right. So to understand more about this light, we need to have a brief overview of the electromagnetic spectrum. So on the left-hand side over here, we have our gamma rays. So our gamma rays have our highest energy, they have our shortest frequencies, our shortest wavelengths, and they have our highest frequencies. After that, we move on to X-rays, which have slightly longer wavelengths, as you can see over here down there, slightly longer wavelengths, slightly lower frequencies, and they have lower energies as well. And so on, this pattern continues. We get to ultraviolet, which is responsible for like skin cancer, black lights, and some other technology that we have as well. And then finally, we get to our favorite region, which is the visible light region. So the visible light region spreads from 400 nanometers all the way to 700 nanometers in wavelength. So over on this side, we have 400 nanometers as wavelength, and I'll draw it out right here. Okay, so over here, this color that we see on the left-hand side of the visible spectrum is violet. And over here, on the right-hand side, over here, we have red. All right, and red corresponds to a wavelength of 700 nanometers. And you can tell that red corresponds to 700 and violet corresponds to 400 because, as we can see, there is a pattern where the wavelength tends to be getting longer as we move towards the right. So continuing on with our pattern, we go from visible to infrared light, and from infrared we go to microwave, and so on to radio. And radio light has the lowest energy, the longest wavelengths, and the shortest frequencies. All right, the longest frequencies, or the lowest frequencies. All right. The wavelength and frequency of a light are inversely proportional to each other, as shown by a famous equation. And this equation tells us something. It's known as C is equal to lambda V. All right. So lambda is the wavelength of that light, and V is our frequency of that light, and C is a constant, which is the speed of light. So it is basically telling us that the wavelength of a light times the frequency of that light is equal to the speed of light. All right. And you can see, if you're still confused about what wavelength and frequency are, here's a very brief summary. So wavelength is basically the distance between two identical points on a wave. So you look at this wave over here. Find two identical points on the wave. I'll just be taking, for example, this point, and then we need to find an identical point. So we go over to this point, which is also identical to that point. So the distance between these 2 points is our wavelength, which I'll call lambda, right, as according to the equation. And our frequency just tells us how many times the wave passes through a specific point in 1 second. So if I isolate this point over here, and then I let my wave run, and I count how many times a full wave runs through that point in 1 second, that would be our frequency, all right? So now, more on the speed of light. So the speed of light can be written as 3.0 times 10 to the power of 8 meters per second. So meters per second can be written as meters per second, and it's written in math over here. So m over s. So m times s to the power of -1 is m over s, right? So wavelength has units of meters, but since we're talking about light waves, it usually has the metric prefix nanometers. So we technically use nanometers more than meters, even though the standard unit is still meters. All right? And now, there is another important equation that we need to consider, and it is Max Planck's equation. So Planck discovered this equation that relates the energy of a wave and the frequency of a wave. So energy, obviously, is E, as we wrote there, right? E is equal to energy, and HV is equal to the Max Planck's constant times our frequency. So H, which I'll describe in the next video, and I'll go into more depth about this equation, including an example. This is directly tied to Einstein's equation, E equals to mc squared, and can help us understand more about how the atom is actually organized. Alright then, I'll see you guys next time. Bye bye.